Hey guys, my name is Tensor. Welcome to another Introduction to Elixir tutorial video. Today we're going to be talking about control flow, which essentially means that we're going to be talking about pattern matching. Now, pattern matching is a very important concept in Elixir, so we're going to be looking at a lot of different examples, and we're going to be really defining what pattern matching is so that you guys can understand the concept and use it to your advantage. I mentioned before briefly that the equals operator in Elixir is not actually the assignment operator. So in most programming languages, if you say x equals 10, then you're assigning the value of 10 to a variable x. The difference here is that the equal sign is not actually assigning the value 10 to the variable x. Instead, this equal sign is pattern matching the value 10 to the variable x. Now, to really understand what pattern matching is, let's look at something a little bit more complex. Person equals a tuple of John and 25. And right now, we're sort of treating this as something that's similar to an assignment. The reality is that there's something a little bit more complex going on here. At the runtime, the left side of the equals operator is matched to the right side. So the left side is a pattern, whereas the right side you have an expression that evaluates to an Elixir term. In this example, you match the variable person to the right side term of the tuple of John and 25. In other words, a variable always matches the right side term and it becomes bound to that value of that term. Person is matching this tuple and therefore person binds to the tuple. We can extend this even further by doing something like this, saying a tuple of name, age equals person. And this expression is equivalent to something more like this, where we have a tuple of name and age and we pattern match it to a tuple of John and 25. So this expression assumes that the right side term is a tuple of two elements. When the expression is evaluated, the variable name and age are then bound to their corresponding elements in the tuple. So if I go ahead and I type in name, you can see that we actually get back the string John, and then if I type in age, we get back the number 25. The pattern here is a tuple with two values. The right side is an expression which is a tuple with two values. Therefore, these two variables bind to each of their respective elements. This feature is extremely useful when you call to a function that returns a tuple and you want to bind the individual elements of that tuple to separate variables. And this is what you might call destructuring, where you're able to take a collection and then destructure it down into its individual components. Here's a good example of calling a function that will return a tuple. The local time returns the date and then the time, and as you can see here, we can pattern match these two so that we can then destructure the date and the time and then use them in any way that we want. So now date equals 2019 4/29, and then time will equal a tuple of 19, 8, and 35. And of course, we can go even further and destruct these values into their individual values. Now notice, if the pattern, which is on the left side, doesn't match to the expression on the right side, then you're going to get an error like this. We have a string, and we're trying to match it with a tuple of two elements. There's no way to really break the string down into a tuple of two elements, and therefore it doesn't match. Finally, it's worth noting that just like any other expression, the match expression also returns a value. The result of a match expression is always the right side term that you've matched against. When we match name and age inside of a tuple to John and 25, then the return value here is just John and 25. We can also pattern match constants. So I can say something like 1 equal 1, and this will then return 1, which is the right side expression. Now, while matching constants in this way doesn't really have many practical benefits, it does illustrate that you can place constants on the left side of an equal sign, which proves that the equal sign is not really an assignment operator. This idea of using constants in the pattern matching can be very useful when it comes to complex matches. So here we take a tuple of an atom of rectangle and then two numbers and bind it to a value rectangle. And then we can destructure that rectangle by using an atom rectangle as a constant here. And this allows us to just take the values 10 and 20 and put them into width and height like this. What it also allows us to do is verify that the first element in the tuple that we're matching against needs to be this rectangle atom. So we're essentially just expecting a three-term tuple where the first term of the tuple is the rectangle atom. This is actually a pretty common idiom inside of Elixir because many functions will return a tuple where the first element will either be an atom of OK followed by the result, or an atom of error followed by the error that occurred. An example of this is calling the file.read function. This will read in a file, and if it does find the file and it's able to open it and read it, it will give us back a tuple of OK, and the second item will be the contents of the file. In this case, the file doesn't exist in our directory, and therefore we do not get a match here. Trying to match on OK and contents won't work. I can match on error, reason, and now reason is bound to this atom. It's important to note that whenever we have a variable that exists in the left side of a pattern, it always matches to the corresponding right side term. In addition, the variable is bound to the term it matches. And this is important because occasionally we're not actually interested in a value from the right side term, but we still need to match on it. So say for instance that we just want to get the time, calling the calendar.localTime function. We can put an underscore here, and what that will do is it will allow us to pattern match to this function, because it's going to return a two-item tuple, and throw out the first item in the pattern match. So even though when we call the function we get both the date and the time, the only one that's actually bound to a variable is the time. This underscore is what's called an anonymous variable. The anonymous variable works just like any named variable when it comes to matching. It matches any right side term, but the value of that term isn't bound to any variable. And of course, if we want to make our anonymous variable a little bit more expressive, we can just add the underscore to the front of the variable names. If we want to, we can use more than one underscore, and in this case, we're looking at a pattern that is nested, so we want to just get the hour out of our calendar local time function call. And so what we can do is create a tuple here, and inside of the second side of the tuple we have another tuple. So we have a tuple of 2 elements, and then inside of it on the second term we have a tuple of 3 elements. But we only care about the first element of our nested tuple in this case. And so of course hour does have a value of 19, whereas all of the other values just get thrown out. Along with anonymous variables, you can use normal variables multiple times inside of a pattern match. So for instance, I can say a, a equals 1, 1, 1. But if I try to say match b, b to 1, 2, and then 3, we'll get back that this doesn't match. The first element in the match happens, and then when it tries to match the next element, if it's the same element and it doesn't match, then it will throw back the error. Now say we want to create a variable binding. So I'm saying x matches 10, which binds 10 to x. And then I'm going to use this variable binding in a larger pattern match, say the tuple with x, the anonymous variable equals 10, hello. This will come back and match because x and 10 are equivalent. But if I go ahead and I say x, underscore equals 11, hello, this will not match. And the main reason why x is not rebinding itself in this case is because we're using what's called the pin operator. The pin operator allows us to pin the match that is currently associated with a variable. So in this case, we're pinning the value of 10 to x. If I remove the pin operator from x and I try to match it in the same pattern match that we just did up here, you can see that the value of x does reassign to 11. And so of course this pin operator can be extremely useful when you do not want to bind to a new variable and you want to keep the value constant. Now of course with pattern matching, we can of course match lists just like we matched with tuples. So here I'm matching f, s, and t to 1, 2, and 3 inside of a list. And of course we get back 1, 2, and then 3. And all of the ideas that we've already looked at do apply to lists as they did in tuples as well. So of course we can still use constants, and of course we can still use anonymous variables and such. Generally though, when you're matching on a list, you're often relying on the fact that the list itself is a recursive data structure. So if you recall, we used the cons operator to be able to actually pattern match on the head and the tail of a list. Something along these lines where we said head cons tail equals a list of 1 through 5. The value of head will be the first value in the list, where the value of tail will be the rest of the list. And so of course this is pattern matching, and we can manipulate it with all of the other tools that we've shown before. So if I just need the front of a list, I can just use the cons operator like this along with an anonymous variable, and this will give me the first value in the list, which will be the head. And of course we can do the opposite where we just match an anonymous variable to the head, and then we get the rest of the list with the tail if we just want to pop the first value out of a list. An example where this is useful is, say you have a list of numbers and you want to sort those numbers and then get the minimum number from the list. You can just do a list where you're taking the head, which is just the front, and then you can put the tail as an anonymous variable, and you can use an enum sort on the list here. And what this will do is it will sort the list first, and then it will try to pattern match it. And so accordingly, we get a list back of 1, 2, 3, and 5, and then min here is now bound to the value 1, which is the head of the list. Of course, we can also pattern match on maps. Say we have a map where we have an age atom and a name atom, and we've assigned them to various values. We can set that equal to another map with the same atoms. We can then get the values from this map by putting in variables here. So I put in the variable name and age, and this will then grab the age value and then the name value. And notice that the order in this case doesn't actually matter. So age gives us back 25, and then name gives us back John. It's also important to note that when you're pattern matching on a map, the left side pattern doesn't actually need to contain all of the keys from the right side map. So if I just want the age that's associated with the age atom, I can pattern match with that pattern on an expression where the map contains at least that key. Maps are frequently used to represent structured data, and in such cases, you're often interested in only some of the fields in the map, and so this type of partial pattern matching is very, very powerful. Now, of course, if the key doesn't exist in the map, we will get a pattern matching error. Now, pattern matching can also be applied to binaries and bit strings, but we're not going to really look at that because we probably won't see many examples of this as we continue through this tutorial. The same can also be said when it comes to binary strings. So you can also pattern match using a binary format with a double quoted string inside of Elixir. So for instance, I can use a binary of A, B, C and pattern match it to the expression A, B, C, which will of course bind each of these values to their binary format equivalent. Now we've already seen this, but patterns can be arbitrarily nested. And if we look at this fairly convoluted example, we have a list, we put in an anonymous variable, then we have a tuple with two values in it, and we have a variable here, followed by an anonymous variable, followed by another anonymous variable in the list. We're matching this to a list of tuples where we have two values in each tuple. Now when we come back and we evaluate what gets bound to our name variable, you can see here that the string Jane is bound to this variable. We basically used our anonymous variables to block out this tuple here, this age here, and then the final tuple in the list. Now, as we've seen in all of our examples, we're able to place any expression on the right side of a pattern match. And a consequence of this is that we're able to essentially chain pattern matches together. And so I can do something like A pattern match on B pattern match on 1 plus 3. So when the pattern match happens, the expression on the right side is evaluated. The resulting value is matched against the left side pattern. The variables from the pattern are bound, and then the result of the match expression is the result of the right side term. And so in this case, the expression 1 plus 3 is evaluated. The result 4 is matched against the pattern B, wherein it's then bound to the variable B, and then the result of the inner match is matched against the pattern A. So consequently, both A and B now have the value 4. Here's a more useful example. So we can call our calendar.localTime function, which gives us back a tuple of 2 tuples, and we can say datetime equals, and we can then put in a pattern so that we only get the hour out. And what this allows us to do is save the entire expression or the evaluation of this function into datetime, but also just get out the hour. Now we're more or less done with basic pattern matching. Let's kind of look at how we can apply pattern matching to function arguments. So here we have a function called area, and the area is taking a tuple in as its argument, and we're pattern matching on that tuple as it's coming into the function. So we're saying, all right, pattern match on the tuple, bind that tuple's values to A and B, and then this allows us to then multiply these two values together. So now I can go ahead and call that function by calling the module.function, and I can pass in a tuple of say 2, 3, and then 2 will be multiplied by 3 and we'll get back the value 6. So what essentially happens here is that when we call the function, the arguments that we provided are matched against the patterns that we specified in the function definition. The function in this case expects a 2-element tuple and then binds the tuple's elements to the variables A and B. This idea of function argument pattern matching allows us to overload functions to create multiple clauses. Now a clause is just a function that is specified using the def construct, and we can provide multiple definitions of that same function with the same arity, as long as the function uses different patterns. As an example, we can re-implement our area function by making 3 area clauses. So here we have an area function that expects a tuple where the starting element of the tuple is the atom rectangle, and then it's followed by 2 other elements. And then what we do is we multiply those 2 other elements together. Then we have an area for a square. This only expects a tuple of 2 elements, where the first element is the atom of square. And then we have another area function of arity 1 that expects a tuple where the first element is circle, and then the second element is the radius of the circle. All of these clauses make up an area function of arity 1, and we can then pattern match against these various different area functions to call the appropriate area function given the data that we're actually passing into the function. We can come in here and call geometry.area and then pass in a tuple where the first element is an atom. So first we have the circle, and then this invokes the area clause that corresponds with this pattern. And so we get back 12.56636. And then we have the square, which gives us back 400 when we put in square and 20. And then we have rectangle, which gives us back 600 when we put in 20 and 30. Of course, if I try to put in a different atom, say triangle, and then I put in values for the triangle's area, we're going to get back that there is no function clause that matches this pattern. So when we call these functions, the runtime goes through each of the clauses in the order that they're specified in the source code, and this is actually important. The order actually matters in Elixir. So it goes through the source code in order, and it tries to match the provided arguments to the function definition. And the first clause that is successful, that is the first clause that matches all of the arguments, is executed. And so if I want to, I can come back into our module geometry and add a fourth clause, which will act as a catch-all. We go through rectangle first, square second, then circle third, and then finally we come down to this unknown call. And then what this does is it takes whatever we've passed into the area function and then passes back a tuple with the atom error inside of it, followed by unknown shape, and then whatever we've passed into the function. So now when I call triangle with our geometry.area function, you can see here that we get back error, unknown shape, and then it gives us back the arguments that we passed in. Alright guys, well that's it for today. I hope you enjoyed this tutorial. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you dislike this tutorial, then by all means downvote it as much as you like. Have a good night.